In this video, you're going to learn about the work-energy theorem. There is a need for a relation between work and energy because force is a vector quantity, work and energy are scalar quantities. So, it is easier to deal with scalar quantities such as energy than to solve a system using Newton's laws of motion. The energy we mention in work energy theorem is kinetic energy. Let us revise about kinetic energy. For any object having mass m moving with velocity v, the kinetic energy is equals to half mv square. It is a scalar quantity, and just like any kind of energy, its unit is joule, denoted by capital J. The relation between work and kinetic energy is introduced using this statement. Work done by a net force on an object is equal to the change in kinetic energy of the object. So, whenever there is a change in the kinetic energy of the object, that can be related to the work done by a net force. This statement, this relation is called as the work energy theorem. Now, mathematically, let us say a net force F creates a small displacement ds and a small amount of work dw is done. Now, according to Newton's law, force is mass into acceleration, that is dv by dt, ds as it is. ds by dt, rate of change of displacement, is nothing but velocity, so dw is nothing but mv dv. Integrating this, we get the total work done. We shall integrate this from initial velocity to final velocity. M is a constant, so integrating for v dv. Integration of v dv is v square by 2. Apply the limits from u to v. We get 1/2 mv square minus 1/2 mu square. 1/2 m velocity square being the expression for kinetic energy. So, here it is clear that the work done here is the change in kinetic energy final minus kinetic energy initial. So, we can say that work done by all the forces equals to change in kinetic energy. But what about conservative forces? Now, so we can say that work done by all the forces is the sum of work done by conservative forces plus work done by other forces such as friction. So, substituting that over here, we get work done by other forces is nothing but change in kinetic energy minus work done by conservative forces. Now, we have previously established that minus work done by conservative force is nothing but stored in the form of change in potential energy, and therefore we get work done by other force is equals to delta K plus delta UC, that is the change in potential energy due to conservative forces. Now, based on the conservative forces, we know this term delta UC will have two components, one for gravitational potential energy and another for elastic potential energy. So, our final expression will be work done by other forces will be the sum of change in kinetic energy, change in gravitational potential energy and change in spring elastic potential energy. Mathematically, delta Ug will be equals to gravitational potential energy final minus gravitational potential energy initial. Delta Us, change in spring elastic potential energy, will be equals to final value of spring potential energy minus initial value, and change in kinetic energy will be equals to final kinetic energy minus initial kinetic energy. Now, this is a very general expression. Based on the question you are given, you have to use some or all of the terms involved over here. Let us see an example to see how this can be applied. A uniform chain of length L and mass m overhangs a smooth table with its 2/3 part lying on the table. find the kinetic energy of the chain as it completely slips off the table. So we have arrangement like this. A chain of entire length L. 2/3 part is lying on the table, so the part hanging will be L by 3. Note that the term smooth table over here implies that you have to ignore the frictional forces of the table. We will find the final kinetic energy as the entire chain slips off the table. So let us assume edge of the table as our 0 level. At this point situated at a distance x from this 0 level, we have a small element of length dx having mass dm. So since it is of uniform density, we can write dm upon dx equals to m upon L. So instead of dm, we can write m upon L into dx wherever it's necessary. So the first thing we do here is to find the potential energy of this element. Small potential energy of that element will be equals to minus dm into gx. Minus sign because our 0 level is over here and we are going downwards. Substituting for dm, we get equals to minus m by L into dx gx. Now to find the total initial potential energy of the length hanging, we integrate from 0 to L by 3 for du. Minus m by L into g constant. So we have to integrate only from 0 to L by 3 for x dx. Integration of x dx is x square by 2. And we apply the limits only to the variable from 0 to L by 3. We get minus mg by 2L L square by 9. That simplifies to having the value of initial potential energy as minus mg L upon 18. Now, when the chain completely slips off the table, then we have the final potential energy that will be equals to minus mg by L. Now the same expression we will have to integrate from 0 to capital L, the entire length. Again, skipping the mathematical part here, integration of x dx is x square by 2. Applying limits, we get minus mg L square by 2L. That will be equals to minus mg L by 2. That is our final potential energy. Note that initially the chain was at rest, so initial kinetic energy is 0. There are no other forces acting on the chain but only its weight that is pulling it down. So work done by other forces is 0. We only have the gravitational potential energy acting over here. So our final expression, work done by other forces plus initial kinetic potential energy, will be equals to the sum of final kinetic and potential energies. Substituting the values, work done by others is 0. Initial value substituted over here. Final potential energy we just derived as minus mgl by 2. Final kinetic energy as it is. Simplifying the expression, we get 8 mgl by 18. Again cancelling out, we get the final expression for kinetic energy will be equals to 4 mg L by 9. And this is the expression that you were looking for.